Welcome to AI Frontiers, where we explore the fascinating world of computation and language, often abbreviated as cs.CL. This cornerstone of modern artificial intelligence focuses on the intersection of computer science and linguistics, encompassing natural language processing, machine translation, speech recognition, and text generation. Imagine waking up one morning to find that your virtual assistant has not only scheduled your day, but also written a beautifully coherent email to your team, summarizing yesterday's meeting with uncanny accuracy. This isn't science fiction. It's the promise of computation and language, a field that's rapidly transforming how we interact with technology. In this episode, we'll navigate the complex landscape of cs.CL, where computer science meets linguistics. We'll explore some of the most cutting-edge research themes, groundbreaking findings, and innovative methodologies that are shaping the future of this field. From tokenization biases to knowledge retrieval and visual grounding, we'll uncover how researchers are tackling the challenges of making machines understand and generate human language. Computation and Language, or cs.CL, is all about developing algorithms and models that can understand, interpret, and generate human language. Think of it as teaching a computer to speak, listen, and write as humans do. This field is crucial for applications like virtual assistants, language translation tools, and automated content creation. For instance, every time you ask Siri a question or use Google Translate, you're interacting with technologies born out of cs.CL research. The significance of cs.CL lies in its potential to revolutionize how we interact with technology. By making machines understand and generate human language, we open up a world of possibilities. In our analysis of recent archive preprint server papers, several dominant research themes have emerged. Let's dive into the compelling theme of tokenization and language modeling. Tokenization is the process of breaking down text into smaller units, like words or subwords. Researchers are continually refining how language models process and understand text. For instance, Pietro Leschi and his team explored the impact of tokenization bias on language models. They found that the inclusion or exclusion of certain subwords can significantly affect model outputs, sometimes increasing the probability of certain characters by up to 17 times. This highlights the critical role of tokenizer selection in language modeling. Next, let's explore knowledge retrieval and integration. This involves integrating knowledge from diverse sources to enhance language models' capabilities. Pralay Ta and his colleagues developed methods for constructing knowledge graphs from unlabeled neuroscience research corpora. By doing so, they improved knowledge discovery and retrieval, achieving an impressive F1 score of 0.84 for entity extraction. This work is crucial for fields with limited labeled data, like neuroscience. Another significant theme is visual grounding in GUI agents. This theme explores the interaction between visual and textual data to improve GUI agents. Qianhui Wu and his team introduced GUI acting, a method for coordinate-free visual grounding that enhances the performance of vision language models in GUI tasks. This work demonstrates the potential for more intuitive and effective human-computer interactions. Reinforcement learning in LLMs is being used to enhance the reasoning capabilities of large language models. Yinji Wang and his colleagues proposed CURE, a framework that co-evolves coding and unit test generation capabilities in LLMs. This led to improved code generation accuracy, showcasing the power of reinforcement learning in this context. Several groundbreaking results from these papers are worth highlighting. First, Pietro Leschi and his team found that tokenization bias can increase the probability of certain characters by up to 17 times. This underscores the importance of tokenizer selection in language modeling. Second, Pralay Ta and his colleagues achieved an F1 score of 0.84 for entity extraction, by constructing knowledge graphs from unlabeled neuroscience research corpora. This improved answers to over 54% of questions, showcasing the power of knowledge graphs in enhancing knowledge retrieval. Third, Qianhui Wu and his team demonstrated that GUI actor outperforms previous state-of-the-art methods on multiple GUI action grounding benchmarks. This highlights the effectiveness of coordinate-free visual grounding in enhancing the performance of GUI agents. Fourth, Yinjie Wang and his colleagues showed that CURE, their reinforcement learning framework, significantly improves code generation accuracy in LLMs. This finding underscores the potential of reinforcement learning in enhancing the reasoning capabilities of large language models. Fifth, Georgia Glisera and his team found that their multi-agent framework improves performance across various English dialects in privacy policy question-answering systems. This work is crucial for creating more inclusive and effective language models. Several common techniques are employed across these studies. First, reinforcement learning is widely used to improve the reasoning capabilities of large language models. For example, Yinjie Wang and his team used reinforcement learning to co-evolve coding and unit test generation capabilities in LLMs. This technique is powerful, but relies on the quality of the initial models. Second, knowledge graphs are a powerful method for integrating diverse knowledge sources. Pralipati Ta and his colleagues used this technique to enhance knowledge retrieval in neuroscience research. However, constructing knowledge graphs from unstructured data can be challenging. Third, visual grounding involves localizing screen regions for action execution based on visual content and textual plans. Qianhui Wu and his team introduced GUI actor, which uses an attention-based action head for coordinate-free visual grounding. This method is effective but requires sophisticated algorithms to function properly. Now, let's dive into 3 seminal papers from this year's research. The first paper is Causal Estimation of Tokenization Bias by Pietro Lessi and his team. The authors aim to quantify the impact of tokenization bias on language models. They defined tokenization bias as the mismatch between the choice of tokenizer and the probability assigned to the underlying character string by the model. The study employed a regression discontinuity design to estimate the causal effect of including or excluding a subword in a tokenizer's vocabulary. This involved comparing similar subwords around an arbitrary cutoff point in the tokenizer's vocabulary. The results showed that tokenization bias consistently affects model outputs across scales, vocabularies, and tokenizers. Notably, the presence of a subword in a small model's vocabulary can increase its character's probability by up to 17 times. This work highlights the critical role of tokenizer selection in language modeling. It underscores the need for informed design choices to mitigate tokenization bias, making it a significant contribution to the field. The second paper is Entity-Augmented Neuroscience Knowledge Retrieval Using Ontology and Semantic Understanding Capability of LLM by Pralipati Ta and his colleagues. In this podcast, we bring you the latest breakthroughs in computer science and AI straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer. This video uses archive.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive.org.